So this last question says, for bike B, how high will the pebble be off the ground after it's traveled 0.1 kilometers? Now I just want to remind you that the graph looks like this. And so bike B is the one that has the 50 centimeter diameter and has a period of 0.5 seconds. That 50 centimeter diameter is in particular important because, or of particular importance, because that is going to help us out in what we're trying to solve. I want to introduce you to a concept here before we start doing this whole question with about I could find if I knew. It's going to help us come up with a strategy. I could find if I knew. And so let's just go ahead and draw our bicycle wheel. This bicycle wheel has a diameter of 50 centimeters. And not that big. There we go. And if it has a diameter of 50 centimeters, we should be able to think about I could find the height above the ground if I knew what? Well, if I knew, well, maybe an angle. If I told you an angle, some angle from maybe here around, I should be able to solve that height, right? I use that, or I can do that using the cast rule and SOHCAHTOA. All right, well, I could find the angle how? Well, I could find the angle if I knew the exact number of rotations. It's not going to be a whole number, but if I knew the exact number of rotations. Well, how would you go about doing that? Well, the exact number of rotations is the distance traveled divided by the distance for one rotation. So the exact number of rotations, if I knew the total distance and the distance per rotation. And I know both of those. And so what I can do is I can now work this backwards. So I'm going to do this as my first step. This is my second step. This is my third step. And this is a great way to problem solve anytime, not just for a situation like this, but anytime. When you literally say, okay, what do I know? Work it, next step. Okay, if I knew that, that'll allow me to find this. And you kind of work through it, and then as you work backwards through the steps, you then have to carry out the steps in the reverse order. So the first thing we're going to do, step number 1, is the exact number of rotations. As I said, that's going to be equal to the total distance divided by the distance per revolution or per rotation. And so we know the distance per revolution, it's pi times r, right? And we know that the total distance in terms of the same units, we need the same units. So we know this total distance is 0.1 kilometers. Well, 0.1 kilometers, if we just do some unit analysis here, and I compare it to a ratio of kilometers, 1 kilometer is 1,000 meters, okay? We also know that our distance per rotation is in centimeters. So let's continue to take this into centimeters. Right now, by doing the multiplication, we can get it into meters. If I take it one more step here, and I have meters here and centimeters here, there's 1 meter is 100 centimeters. So in other words, you're going to take that 0.1, you're going to multiply it by 1,000, and then you're going to multiply it by 100. And that gives us a total distance of 10,000 centimeters. So we have 10,000 centimeters. And then when we calculated the distance or the speed that the bike was traveling, we determined that pi times 50 gave us 157.0796. That was pi times 50. And so now that's all in centimeters. So that's good. We have them in the same units as we need. And we get 63.66 rotations of the wheel. Okay, so there's the first step. We've got the number of rotations. That's a great starting point. The second thing we need to do is determine the angle. Well, the angle equals, it can be determined by 0.66 of a rotation. And that's because after 63 rotations, we're back right to where we started. And again, let's look back at the graph really quickly and remind ourselves that bike B starts at the ground. From the ground. So we're starting from the ground, and I noted here that it could be from the positive x-axis, but because we're going from the ground, it's actually from here. The angle is going to be measured from the ground, from there all the way around. So 0.66 of a rotation. Well, a rotation would be 360 degrees. So it's 0.66 times 360 degrees, which gives us a number of degrees of 238 degrees. And so now we have an angle. We know it's 238 degrees all the way around from the ground up and around. And so that's going to be somewhere more accurately drawn like this. If it's starting at the ground and it went around 90, 180, 238 is somewhere about here. So what we're going to have to solve here is we're going to have to solve this, this height here, h, but then we're also going to have to add to that 25 centimeters there because that's where the axle height is. The height that we solve here is going to be the height above the axle height. So if this is 238 degrees, that means that this related acute angle beta is going to be 270 minus 238 degrees, or a total of 32 degrees. So what I'm going to do is, now that I know that angle, I know that the radius of this wheel is 25 centimeters. That's the radius. So I can say that I know the opposite side. I'm trying to solve actually the opposite side. I know the hypotenuse. That allows me to use sine. So sine of 32 degrees is going to equal the opposite side, which is the height, over the radius, or the hypotenuse, which is 25. And then it's just a matter of saying, well, then 25 times sine of 32 is the height, and the height is a value of 13.2 centimeters. So we can conclude, therefore, after 0.1 kilometers, the pebble is 13.2 plus 25 centimeters above the ground. In other words, it's a total of 38.2 centimeters. Now you could carry a few more significant digits, a few more decimal places than I did there, but that's the idea of how that's done. And so that was the third thing there, was the height above the ground if we knew the angle. So that was step number 3 right there. So there you go. We've got 38.2 centimeters above the ground. We know how fast each of the wheels is moving, which is the same speed. And so the last thing that we're asked to do is simply reflect. How would changing the speed of the bike affect the sinusoidal graph? I want you to pause the video here, think about both these questions, and then when you've thought about them, come and see my answers. Here's your answer. Changing the speed would affect the sinusoidal graph because that would change the period if the radius of the bike is constant. Change the period if the bike radius is constant. And the second question that says, for a third rider traveling at the same speed but on a bike with a larger wheel than bike A, how would the graph of the resulting sinusoidal function compare with that for bike A and bike B? Well, if it had a larger diameter, that means it would have a larger amplitude. And that would also mean that it would have a longer period. Just as you look above, we notice that bike A, which had a 60 centimeter diameter, had a period of 0.6 seconds, and bike B, that had a diameter of 50 centimeters, had a period of 0.5 seconds. So likewise, if we had a bigger or a larger diameter, we have a larger amplitude, we have a larger period than both of those if it was moving at the same speed. So there you go. If you have questions, as always, reach out and please ask for help. I'm happy to help.